Okay, the last part to lesson 1 is on the characteristics. This is a big one. This has a lot of information in it. So we're focusing on what I consider like the personalities, right? They all have a very specific characteristic and they have some words and vocabulary that you need to know in order to describe the characteristics and describe the polynomial. Okay, so this is on 6.2. So you have in this, keep in mind, you have all these characteristics kind of explained, but I'm going to go ahead and explain them to you, and hopefully it'll make some sense to you between the keep in mind and what I tell you. You have in your packet that I photocopied for you, you have all these characteristics defined for you. So I'm going to go over them, and you can write yourself some notes, and then we'll go over a couple of the examples from the book, and I'll just talk you through those. Okay, so this is a list of all the characteristics for polynomial functions that you need to be able to tell me. The first one is the degree. All right, the degree is the highest exponent. So we saw that the polynomials have to have whole numbers, no negative exponents. And so the largest exponent is what dictates the degree. And the degree will dictate what the name of it is. Okay, so if you only have 3 choices. If you have a degree of 1, then it's a linear. If you have a degree of 2, it's a quadratic. And if you have a degree of 3, it's a cubic. And when we get to the example, we'll point out where the degree is. But just for now, the degree is going to name it. The leading coefficient is the number in front of the term with the greatest exponent. So we talked about them being an adding of monomials. So you're going to take that single expression where you got the degree, that largest exponent, and the number that's in front is called the leading coefficient. Coefficient is just that number. You will need to be able to tell me the number of x-intercepts. The best thing to do is just look at it. Get a graph, produce a visual of it, and see how many times does it cross the x-axis. The x-axis is the horizontal. How many times does it pass through it? And then the y-intercept is the coordinate where the function crosses the x-axis. So you'll want to know vertically where is it going through that. And that point's actually a really important point in terms of modeling. People want to know what that point is of quite a bit. A turning point is the number of times it changes directions. So if you have, for example, a function that looks like that, this is a turning point. It changes directions. Also called a max or a min, because it comes up and then it's going to turn and go back down. So it's creating that turn. The end behavior, there's a math definition for it, but I'm going to go with a non-math definition. So the non-math definition is we're going to think about where the ends of the function are. Right now, to do that, I want to go over the quadrants. And so they're based on what are called the quadrants of a grid. So if I have a grid, an x and a y, then we name the grids, and we start with this upper right-hand grid quadrant, it's called, is the first one. And that's where everything is positive. That's why we start there. And then we go in a counterclockwise direction, and we just name them 1, 2, 3, 4. Okay? So you want to have that, whenever you're talking about the end behavior, you'll want to have that in your mind or have a picture of that close by. So what we think about is, again, if we're going to read a function like we read a book left to right, I'm going to think about where does it come into the grid and where does it go out. Right? I know that it goes on forever, but because we're human, we have to have ends to things. For me to put it on my paper, I'm going to have a grid. So I always think of it, well, if I'm coming in from the left, it's going to have to come in either quadrant 2 or quadrant 3. So where is it coming in? And then it's going to keep on going, and it's going to have to go out 1 or 4. Where is it? Which way is it going out? And that's called the end behavior. The domain and the range are what we call their defined functions. For polynomials, It's pretty simple because everything is defined in a polynomial function. So sometimes it's easier to think about when it's not defined. And so when we talked about the continuity piece, where if a function is not continuous, if I had to lift my pencil to get to the other side, like to continue on with it, when I've lifted my pencil and put it somewhere else, that means now I have some values in there that have no definition. There's a gap there. Polynomials have to be continuous, so everything has to be defined. And that's what the domain in the range is telling us, is that everything is defined. We are continuous. I'll give you some more mathematical ways of writing that when we get to that point. But that's just compared with this idea that it has to be continuous. I'm not eliminating any values for x's by lifting up my pencil and having to get to another part to it. I'm not hopping over any values. Okay, now the one that we're going to do together is on page 158, example 1. It's going to give you two polynomials, and then you're asked to write down the characteristics. And they have it in as a little tip here as to what you're supposed to do. I've created a table because to me it makes more sense, a little more organized. The table and then I'm going to list the characteristics in the table. So if you want to pause this and write down the table, it's all the ones that we've already talked about that I just went through with you. Okay, so the two that we have A and B. I'm just going to split my table down the middle and go through each of these with the functions. First one is the degree. So the degree is the highest exponent, the largest exponent. So in part A, I'll put A here and B here. In part A, we have 4x plus 2. Well, there's a 1 there that, again, you'll never see it written. So the degree of 4x plus 2 is 1. And anything that has a degree of 1 is linear. And then part B, the highest exponent is 2. And if it has a degree of 2, this is a quadratic. So the other one that's not on this example is if it had a degree of 3, that would be a cubic. Now to get the number of x-intercepts, you're going to have to graph it. That's your best bet. So take your calculator, go back into that y equals screen, clear out what you have, and put in 4x plus 2 and hit graph. Get a picture of that real quick. You should see a line. And it's an increasing line, so it's upward, it's climbing, consider it. And when you see it climb on your screen, you should see it go through the x-axis. So the number of x-intercepts is 1. Then go back and, well, let's finish off these with this. While we have a picture of it, let's go ahead and finish off these characteristics. So I still have my line on my screen. The y-intercept, it's hard for me to read it from my calculator. So even if I put my glasses on, because my eyes aren't as good, I still have a really hard time reading it. So I want to know a different way of figuring that out. So the y-intercept is that last number. It's called the constant term, right? And it's written 0, 2, because you went 0 on the x and you just went up the y-axis 2. The leading coefficient, so I got my degree from the 4x because the one exponent was with the 4x, so that means the leading coefficient is 4. And the end behavior, so again, I'm going to go back to my graph and look at my end behavior. So if I put back that one here, if I think of it as a grid, all right, and I can do it on my calculator, but I'm thinking I'm going to read it like a book. I'm coming in here. Well, when I come from the left, it's coming from quadrant 3. And from quadrant 3, I can think about tracing it, and it goes out quadrant 1. So the end behavior, I would write Q3 to Q1, quadrant 3 to quadrant 1. That's how the end behavior works. And the domain and the range, well, let's go to the number of turning points. So again, if I look at it, I want to think, can I see any time that it turns? Does it have that curve? And a linear function doesn't, of course, because it's a line. Right? So there are none. All linear functions don't have turning points. And then the domain and the range, I said I'd show you a more math way to write it. And so people call it XER or YER. And what this means, you can go back to your set theory time. This means all the X values that are a member of real numbers. Right? So it means we haven't taken any out of them. They're all included. It's continuous. And so that we write that for X and Y. There is a non-real number system, but we live in the real world. You can think of it like that. But it also means that it's continuous. There's not any hopping that's going on or gaps. Okay, so we'll go back and do the quadratic one. So this time I'm going to produce the picture in my calculator. So I'm going to go back to the y equals screen and hit negative 5x squared. Hit the negative, not the minus. Plus 2x, and then subtract 1 and hit graph. Okay, and then I'm going to get a picture of it up here. Kind of looks something like that. Doesn't have to be perfect, just to give a general idea of what it looks like. Okay, the number of x-intercepts. Now in this case, when I'm thinking about where does it cross the x-axis, this particular quadratic doesn't. Now that doesn't always happen. This could be up here. It could be like this, like the ones in your picture and your keep in mind. It might go through it twice, right? Or it could go through it once. Get a picture of it though. The minute you get a picture of it, you'll be able to visually see how many times it crosses the x-axis. And then the y-intercept, there's always one y-intercept. There's always, in all these polynomial functions, you're always, unless it's a vertical line, you're always going to have it go through the y-axis. And so we can see it here. You don't have to read it perfectly. From the graph, it would be hard, but I know my trick. My trick is, I'm going to highlight it. If I want to find the y-intercept, I'm going to look at that last number. So I really don't even have to try to struggle with reading what it is on the graph. If I have the equation, I can read it from the equation. If you don't have the equation and it's not super clear to you, estimate it. The leading coefficient, so the leading coefficient is this number that's in front of the squared term. Right, I got my degree from negative 5x squared, so the leading coefficient is negative 5. End behavior, so I'm going to read it like a book. I'm going to come in from the left. It's coming in quadrant 3. I can trace it, and it comes out quadrant 4. So the end behavior, Q3 to Q4. Domain in the range, since when I traced it, I didn't have to hop. It's continuous. So that means all of my x's and the y's are being defined. And then number of turning points. So quadratic does have a turning point, so I can see it. It comes up, comes to this high point, and then goes back down. So it does have 1. Okay, so that is the rundown of the characteristics. So it's time for you to practice. On page 158, this is another example. So on page 158, example 2 is a matching exercise. So to do the matching exercises, you're just going to produce the picture. So you want to match the graph to the equation. So if you produce this in your calculator, you'll be able to see which one it is. And so if you want to pause and do that real quick, and then I'll come back and identify it for you, although the answer's in the book. So when you produce the graph of x squared plus 3x minus 1, it goes to graph E. And negative x squared plus 3x plus 2, that goes to graph A. Gives you the explanation down here. It talks about the turning points and the end behaviors. This one, right, one's up, one's down. You should be able to visually see which one matches. Okay, so now it is time for you to practice. On page 160 to 161, you're just going to do numbers 1 and 3. They're pretty big ones, though. They're long ones. So it says match each graph with the correct polynomial function, provide your reasoning. And underneath it, it has a bunch of fill-in-the-blanks. These fill-in-the-blanks are like the table that I produced. So it's for graph A, it says the number of x-intercepts and the y-intercept, the end behavior. So take the time and actually fill out all of this and check your answers to see how much of that has sunk in. But to match it, you're going to put this in your calculator and then see which one it matches. You might be able to kind of narrow some things down just in terms of what type of polynomial do you have, right? Looking at the degree, give it a name, and you could probably pair a couple. But then to go further with that, you're going to need to have this information. So take a minute and do this one, and then number 3 as well. It's a fill in the blank, so much like the table. Okay, so you're going to check your own answers. Hopefully you have. So I'm not going to go over all of this. This is a pretty big problems to go over. But if you have any questions, contact me and I can talk you through some things. But that's your first lesson for polynomials. So you should be, the big idea is that you can identify whether an equation is a polynomial, a graph is a polynomial. If it is a polynomial, it'll be one of the 3. It's only going to be a linear, a quadratic, or a cubic. So hopefully you should be able to tell me which one it is. And then either from a graph, or if I give you an equation, you can produce the graph and you can fill out a characteristic table. Okay? Good luck. You have homework. The practice problems are in your packet, so you can do those just to reinforce your learning.